the, you know, the most perfect formula in mathematics, which I've never really used before, but it is kind of cool that they all together make 0. And then here is kind of what they did in the video is they talked about compounding interest, you know, when n is 12 months or when n is 365 days, and kind of showed you what it approaches. So the only thing you need to put on the front page is 2.7 like 18 ... right? Because it's irrational. It goes on forever. But it is important that you know E is about 2. Because if we were graphing 2 to the x, we know what those values are. If we were graphing 3 to the x, we know what those values are. So 2.7 raised to the x power is a steepness that's just right in between those two, right? But it still would go through 0, 1, and it would have all the same properties as 2 to the x and 3 to the x. It's just in between as far as steepness goes. So on the back page here, it tells you that E is called Euler's number. So it's unclear whether he used E to name it after himself. So I just wanted you to type these couple numbers into your calculator. Like type in E squared. So type second E raised to the second power and see what you get. Just practice, you know, using E on your calculator. E squared would be what, 7.4 if I rounded? Does everybody see where E is to get it? Okay, so E, to the nearest hundredth. So what would that be, 7.39 instead? Okay, try E to the negative first power. That would be 1 over E, right? 1 divided by 2.7. So try second E to the negative first power. And then round that to 2 decimal places. So you get what, about 0.37? All right, so that's all we need to be able to graph E to the x. And I'm not really going to have you graph E to the x much, but it's just the idea that E is just another number. So E to the x. So if I'm at 0, right, E to the 0 power would be 1. So my y-intercept is still 1. E to the first power, well, that's just 2.7, right? Because 2.7 raised to the first power is still itself. And we just said E squared was 7.39, so about here. And we just said that E to the negative first was 0.37, so that's kind of close to the axis. So that's it. It looks just like my other curves of 2 to the x or 3 to the x. What? So I graphed E to the 0 power, anything to the 0 power is 1. E to the first power would just be itself, 2.7. And then E squared was 7.4. And then E to the negative first was about 0.4. So I just used the values that I got. And then I don't want to forget that I have an asymptote at y equals 0, right? So that should be staying above y equals 0. What's the only difference between graph A and graph B? It's hard to see because my font is so little, but there is a minus sign, right, with the x. How does that flip my graph if it makes all the x values opposite? Yeah, so it's just going to take these points and move them over here. And it's going to take this point and move it over here. So you're going to have the decay function, 1 over e, so 1 over 2.7. So we can just take our graph and just flip it around. So I'd have 0.4 on this side, 2.7, and 7 point, whatever that was, like that. Same steepness, just flip over the other direction. And then see if you can do graph C. So think about what transformation it would take graph A to become graph C. And this one's at y equals 0. So what does a plus 2 do when it's next to the x? Shifts everything left 2. So every single point will go left 2. So if I was at 1, now I'm going to be left 2 and still at 1. And then I was at 2.7, so now left 2, I'm at 2.7. And then I was at 7.4, so now that's going to be my y-intercept. Kind of like that. If you take the points and shift them all to the left, doesn't change that my asymptote would still be at y equals 0 though. Does anyone remember what he said about in the video? What 2 interesting facts about the graph e to the x were stated in the video that make it important in calculus? So I'm going to tell you, even though I don't know if all of you are going to take calculus, but if you are the e to the x curve, right, if this is e to the x, basically the 2 things you study in calculus are derivatives. Derivatives are these tangent lines on the curve, and you also study area under the curve. So the second half of calculus is figuring out like how much area is under the curve. So at e to the x, the value, the derivative, and the area are all equal. And they said it's the only function where if you pick any point on the curve, if I pick right here, if that value is whatever, 0.8, the derivative slope is also 0.8, and the area under the curve is also 0.8. So it makes it useful in calculus, and I never really understood that until this year teaching calculus, how much it's used in calculus, but this is kind of the planting of the seed that E even exists. So we're just using it for compound interest this year, but